Okay, next, I would like to introduce hierarchical design. Okay, it's a very important, when we compose a system, you definitely will run into multiple modules and organized in a hierarchical way. Okay, and here I will introduce these things. Stream is a kind of a standard way to connect modules. Okay, and then I will introduce there's a standard structure to design to compose multiple modules. And later I will introduce two cases. One is the reconvergence and one is the feedback path. Okay. Okay, this is a very simple example, simple forward string system. In here, there are three functions. Okay, with input is a string, and internal communication is also string, and output is a string. Okay, so when you try to compose this three module in a data flow structure, then you will use those pragma. Okay, first you specify this module internal is a data flow, and you declare the interface is a AXI string. Okay, and the interface signal you define with this structure, AXI structure. Okay, you can put on any kind of information from outside. Okay, and for the internal string, you create using the string HLS string, you declare the static. Okay, and also you use the pragma string with specify the depth here, and depth is very important here. Okay, because each task may have a different latency. Okay, and this is a simple forwarded, but there might be a reconvergence, and later we will see this case. And oftentimes you need to specify proper depth, otherwise the system won't be run efficiently. And I will also show an example later. Okay, so that's the basic canonical form, standard form to construct multiple modules that run in a data flow. Okay. So this case is you have a multiple level hierarchy. For example, for this is the top module, and then you have a ICOM server. And this one you have a sub module. Inside you have a sub module. Okay. So in this case, for the hierarchical modules, first the sub module need to specify the data flow. As in the previous class, we mentioned the data flow won't propagate to the sub module. So for the function inside the sub module, if we want to do the data flow, you have to specify the data flow. Okay, and also we like this one inline. That means these three modules actually up exposed to the top module. So this ICOM server module will disappear. Yeah. Okay. So for hierarchical module that you use this way. Okay. This is a standard coding style. Yeah. And also for the function at the leaf, what I mean leaf, there's a data flow at the leaf that you need to specify pipeline. Okay. So let's say this function is the leaf function of the data flow. And inside you have a for loop. Okay. Okay. If that's a function and no, you just operation one, operation two. Okay. then no problem, you specify pipeline here. Okay, and if this function has a for loop, you have a for loop, then this for loop you have to specify pipeline. You don't put the pipeline here. If you put the pipeline here, you know the for loop will enroll, right? Yeah, and enroll consume too much resource. Okay, so you actually put the pipeline inside the for loop. And for the function, you have a for loop, but you have a nested for loop. Okay, then I want to put the pipeline at the inner one. Okay, so that's the function inside the function. Yeah, that's the way you structure that. Yeah, and also make sure you enable flush. Yeah, because the loop need to continue the running, the reentry. The for loop ever execute, then you will, will entry again. Then you want to, oh no, there's a flush. Okay, enable flush. That means for data flow, sometimes the input, you don't have an input comes in because maybe previous stage the latency is longer. But for this stage, you want the pipeline continue running to the flush. Yeah. So you also for the pipeline you want to enable flush. Okay. So the summary is the canonical form is for the interface. Okay, you use the interface XIS. For inner function interface, you want to create string, and it's a static string. And you need to specify the depth using the pragma string depth. And for multiple level hierarchy, you need to put the data flow and use the inline. At the leaf function, you want to do the pipeline enable flush. Yeah. At the very leaf, if it's a for loop or nested for loop, you put the very leaf one. That means the very inner for loop. Yeah, and also use the flush. Okay, so that's the basic way you use the data flow to compose your hierarchical module. Yeah, let's talk about something here, reconvergence. As I said, when you compose multiple modules, that first you have two things. One is the rate, or throughput of each task. Second is the latency. Okay, for the rate or throughput in a data flow, the slowest throughput always is a bottleneck. Yeah, so you want to balance each stage of the data flow. Okay, to make sure you got a consistent throughput. Okay, if for certain stage, the throughput you can only do the II equal 2. In that case, there's no reason you want to push other module II 1 because eventually the whole system give you throughput 2, the II 2. Yeah. So you want to try to balance it. Yeah. And in here, the FIFO is introduced to bridge the latency difference between the data flow task. Okay, in this example, you have a block 0 goes to block 1, block 2, and block 1 and block 2 reconverge to block 3. And this 3 module, block 1, this block 1 has a 3T latency because there is a multiplication. But this multiplication latency is 3, but II equal 1. II still equal 1. All the module II equal 1. Okay. Throughput rate is 1, okay? But block 1 has a latency 3, okay? In that case, when we write the code, when you execute, you will find out you got deadlock. In this case, you don't have any FIFO between them, the 0 FIFO, okay? So you can see the block 0 generate the output goes to the block 1 and block 2, okay? And then the block 2 output, the block 2 generate the output, but the output could not flush. So block 2, this block 2 cannot take an input, okay? But the block 1, it cannot take an input, so this guy, the block 1, won't generate output. So the block 1, the input store, and block 1 is not specified with the flash. So when the input store, the pipeline store too. So block 1 cannot proceed. Yeah. In this case, the system simply hangs. Yeah. So the first thing you want to do, you want to make sure the block 1 can flush the data, can continue doing the pipeline. So in this case, you insert the pipeline enable flush. Okay, when you enable flush, so block 1 can proceed. Okay, block 1 proceed, then the block 2 data and block 1 data can be pop, can be used by block 3. So when block 3 finish, okay, yeah, block 0 can running here, okay, but block 0 can only feed the data when block 1 and block 2 can accept the data, which is here. Because block 3 finish the data, it will assert the continue. Remember the continue? Yeah. Okay, so after block 3 finish, that block 1, block 2 can start taking the output. Okay. Yeah. So in this case, you will get the you can see the 1, 2, 3, 4. The throughput rate II equal 4. Every 4 cycle, you produce 1 output. Okay. In this case, there is no FIFO between modules. So next step is we want to put the FIFO. Okay, we want to put the FIFO here. Okay, and this one is latency is 3, and this one latency is 1. Okay, so in this case, let's see what's going on here. Yeah, so block 0 generate the output to block 1 and block 2. Okay, and then once it's taken, then block 0 can run in. Yeah. Okay, and then the block 1, block 2 generate the output. The output actually throw into the FIFO. Okay, so block 2 can take input from block 0. Okay, and since the block 1 is a pipeline, so II equal 1, so it can take. Okay, and then next, coming down here, the block 0 can run, and then it generate, and the block 2 output can pull into the FIFO again. You have a 2-level FIFO. Okay, until this stage, okay, block 3 can run because the block 1 produce the output. So block 3 can take data from block 1 and the FIFO. Okay, and the block 2 output can push into the FIFO because one FIFO pop and also push into. Okay, so in this case, you can generate output every cycle. You can generate output every cycle. And the run-up time means when it starts to the first output produced is a full cycle. So after full cycle, that you can generate output every cycle. Yeah. So in this case, you will see what's the FIFO depth you need to specify here. Yeah, you need minimum 2. Yeah. Okay. So we need to specify proper FIFO to make sure the data flow can there's no stall between the data flow stage. Okay. Yeah. Okay. Let's talk about feedback. Okay. For these things, initially those feedback paths, the FIFO all empty. So you can imagine that the block 0 cannot work in. So this system simply deadlock from the very beginning. Yeah. So you need to pre-initialize the feedback FIFO. Okay, in this case, you preload the feedback FIFO, preload 1. Okay, let me trigger the. Okay, so this one, that's 1T latency, and each one is II equal 1. Okay, and then let's say we preload 1 data here. Okay, let's preload 1 data here. So when you preload, then block 0 can kick off, can run, and then block 1 can run. Okay, but block 0 cannot start until block 1 push input, because the preload data only one data. Okay, and the second data is pushed in by the block 1. So block 0 can start only when block 1 push its data. Okay. So in this case, you cannot achieve II equal 1. Here, II equal 2. The interval, okay, the whole data flow interval is 2. Okay. So let's say we put the preload equal 2. Okay, preload equal 2. Then you can kick off the block 0. And here, block 0, you can start. You get the second preload data. Okay, and later on, the FIFO can produce by the block 1. The feedback FIFO data can be produced by block 1. So in this case, you got the II interval equal 1. Yeah. So in this case, you probably can conclude a rule that how many data to preload for the feedback path. Okay. So if the forward path latency equal X, then you have to preload X data. Yeah. Okay. So I use two simple example. One is the reconversion and one is the feedback to illustrate. But the system can be much more complicated when you design, not that simple one. Yeah. So you need to use VT's data flow analyzer or deadlock analysis tool. Yeah, to properly decide the FIFO depth. Okay, so I finished the 3 PPT. Okay. Yeah, any more questions? Any question?